Hi, my name is Zach G, and I'm a tutor here at Chegg.com/tutors. And today I'm going to be talking to you about the topic of wave particle duality, or how electrons act both as waves and as particles. Okay, and so crucial to understanding how this was with Einstein, and I just wanted to start this video off with a quote from him talking about how difficult this topic was when they were first figuring it out. And he said that it seems as though we must use sometimes the one theory, and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do. Okay, so some wise words from Einstein to start our discussion. So, light as a wave. So here in this picture, I have kind of demonstrated what's called the double slit experiment. And the double slit experiment shows that light, when it goes through a slit, will diffract, and this diffracted light can then constructively or destructively interfere with itself, and these constructive waves will form energy maximums, which we can then visualize on a screen downfield, or energy minimums because of the destruction of the waves, which will turn out to be black space. Okay, and we can use this formula here to determine where at on a screen and how far apart these dots will end up appearing. Okay, and that's just using the distance between the two slits, d times the theta angle away, m being which maximum it is. So this is maximum 1. These both are maximum 2, and lambda corresponding to the frequency of light we're using. Okay, so in this example, we see that light is acting as a wave. Another example is if you think of the collared prisms that show you a rainbow of light, or even a rainbow. That's actually the light going into a different medium, and because of the different frequencies, it separates. Okay. So these are our particles of waves, and this demonstrates that light is acting as a wave, okay? So the problem was that it was fine that light was a wave, but it was showing these weird properties that nobody could really explain. And so Einstein was playing with the photoelectric effect in the 1905-ish time period, and he noticed that when he shined photons, or light, onto a metal surface, electrons would be ejected. According to Maxwell's classic theory, the higher the intensity of photons shined onto the metal, the faster the electron should come off. When they did the experiment, however, the photons didn't come off, or the electrons didn't come off faster, just more of them came off with the higher intensity of light. However, when they switched from using higher intensity light to different frequencies of light, for example, going from like a red light to a blue light to a green light, they noticed that then the electrons did come off with different speeds and different kinetic energies. And so Einstein borrowed an idea that Planck was playing around with, that electromagnetic energy is released in quanta. And by borrowing this idea, he came up with light traveling in photons of energy. Okay? And so now these photons are kind of like a particle, and we've seen previously that light is traveling also as waves. Okay, and so here's the Planck's equation to describe the energy released in quanta, and you can see here that it is clearly dependent on the frequency and not the intensity. Okay, so frequency of light based upon the wavelength and the velocity of it. Okay, so that really explained why they were getting this different effect here in the photoelectric effect. So a few years later, de Broglie came along and said, well, it's good that light is acting as both a particle and a wave, and so electrons are particles and waves, but what about everything else? And so what he did was he took Einstein's equation of E equals mc squared, so this describes particles and how fast they're moving. And then he also took Planck's equation of h, which is Planck's constant, times the frequency is equal to energy. Okay. Now what he noticed was if light was traveling as both particles and as wavelengths, these two energies should be the same. And so he made the assumption that they were and set them equal to each other. Now, because particles aren't traveling at the speed of light all the time, if you think of you or I, or your car driving down the road, we're going at most 15 meters per second. That could be really fast. I'm not for sure. I'd have to, think about that, do the math. But if you think of like 25 miles an hour, that's not very fast. Okay, so it's much less than the speed of light, which is, to the like 8th power of speed, meters per second, really fast. So each plugged in velocity for this because it more represented, us and more particles. So that gave us mass times velocity was equal to Planck's constant times the frequency, or velocity squared. Can't forget our squares. And we know that frequency is equal to velocity over the wavelength. And so he plugged this into here. We're going to plug that here. And that gave us that mass times velocity squared was equal to Planck's constant times velocity divided by wavelength. One of the velocities, we had a velocity on both sides, so we'll lose the square here, we lose this velocity here. And then if we solve for the wavelength, we see that wavelength is equal to Planck's constant divided by the mass times the velocity of that particle. Okay, and so now we've shown that even larger particles, such as our cars, us, everything we see in the macroscopic world, has a wavelength. I mean, we're all made of electrons, so it makes sense since electrons can act as both particles and waves. And so a common question you may think about is, well, how can this be? We don't see, cars going as waves. Well, think about the equation here. Planck's constant's pretty small, and our mass is really large, and so is our velocity. So if we get a small number on the top and a really small number on the bottom, or a really large number on the bottom, we end up with a really small wavelength. And typically we can't see that wavelength because it's so small. Okay, so our understanding of how particles are both waves and particles really all goes back to this wave particle duality thing, where they kind of are both. And at the same time, they're really neither, but they're both. So really we need a little more understanding to understand why these are the way they are and what makes them up. Anyway, this pretty much wraps up my discussion of wave particle duality. If you have any questions, please reach out to myself or any of the other chegg.com/tutors, and we'd be happy to help. I hope you learned something from this video, and I hope that you have a great rest of your day. Until next time, take care.